Thank you. Okay, so yeah, I'm going to talk a bit about the future of artificial intelligence as I see it. And I'm going to start off by talking about, well, I'm going to spend quite a lot of time talking about landmarks in artificial intelligence. And I'm going to spend a lot of time actually talking about a very recent landmark in AI, which is Alphago. Now, how many people already know about Alphago? Yeah, I thought a lot of people would. So I'm going to talk quite a lot about Alphago and how it works, how DeepMind managed to create a bit of code that could defeat one of the world's leading Go players, and what the implications are. What does that mean for how far we are along the road towards human-level artificial intelligence in particular? So that's really going to be what this talk is all about. Okay, so. So first of all, so there's really only I could talk about lots of different landmarks in AI, but there's really only two that I want to highlight. And the first one is this one. So back in 1997, an IBM program created by IBM, and especially designed bit of hardware created by IBM in combination, managed to defeat Garry Kasparov, who at the time was the reigning world chess champion. And of course, that was a very significant achievement in AI. And I think if you told some of the pioneers, some of the founders of the field, that at a certain point, a computer program would be able to beat the reigning chess champion in then they would think that we kind of got there. That would be they would think that this was the pinnacle of a sort of intellectual achievement, and that would mean that we'd sort of achieved human-level AI. Surely, if we can, got a computer that can win at chess, can beat the world champion at chess, then we really have kind of got there. But this, of course, wasn't true. It turns out that in a certain sense, chess is one of those things that is kind of, in some ways, sort of easy for a computer. And the reason it's easy for a computer, easy in scare quotes, whereas it's difficult for human beings, is that computers can tackle chess in this rather brute force way that exploits their computational power. And it's important to kind of like understand how this works, because it also enables us to understand how AlphaGo works and how AlphaGo is special. So imagine that you're playing a game of chess and there's a particular board position that you've got in front of you. Then from that board position, there are a number of moves that you can make. So let's imagine, and so I want you to kind of imagine basically a tree of possibilities. So some of you will be familiar with this concept already. So from your current board position, there's a number of different moves that you can make. And each one of those moves leads to a new board position. And from each of those board positions, your opponent can then make a number of possible moves. And then from each of the board positions you get from there, then you get your chance, and you again have got a number of possible moves that you can make. So I should have a nice big picture of this. There's one coming up later on, but you can imagine that there is a large tree of possibilities that basically stretches out from the current board position into the future that captures the sort of possibilities that are out there. Now, a computer can basically search this tree of possibilities. It can say, well, what if I did that move, and then my opponent did that move, and then it can search down this tree of possibilities, and then it can say, oh, that wouldn't be very good for me, so what if I did that, and he did that, and I did that one, he or she, and then and just basically look through all these many possibilities to find what is a move that is very likely to scupper the opponent. So it involves this kind of search. Now, you can't in chess do a search that will take you all the way to the final sort of checkmate position. So you still have to have some means of evaluating the board positions. So you can search down to a certain depth, but then you get to a point where you need to say, well, that'll take me into a board position which is really good, or that one will take me into a board position which is really bad. So I'll prefer, to angle down this branch rather than that one. So you need some way of kind of assessing the board position, evaluating it. And so, you can imagine very crude ways. You just add up the values of the pieces, that kind of thing. But anyway, those are the basic components of a bit of code to play chess. And then all you need to do to make it outstandingly good at chess is just to have an awful lot of computation that can search through an awful lot of possibilities. And that is, in essence, and of course there's more to it than that, but in essence, that's how Deep Blue defeated Garry Kasparov. Now, that took place in 1997, but the landmark that I'm really interested in is this one. So just back in March, Google's Alphago, Google DeepMind's Alphago program defeated Lee Sedol. So this is Lee Sedol here, looking a bit pissed off with some reason, because I don't know which match this actually is, but as you, I'm sure you all know, Lee Sedol was defeated 4 games to 1 by Alphago, and after the third game, DeepMind's Alphago was basically 3-0 up. So after the third game, it had won. But unlike tennis, it's really painful. You know, it's best of 5. But even though the poor guy has lost, you know, he has to kind of play the last 2 games anyway. And but then he won the 4th game, and that was for those of you who followed it, it was really actually very moving that he won the 4th game, because by that time, despite all the kind of predictions of the commentators who thought that you know, there's no way that you can defeat Lee Sedol in Go, but by game 3 they were thinking, my God, this program has divine powers, and then so when Lee Sedol finally managed to defeat it, it was a wonderful moment, you know. Then he lost the 5th one, so it's 4 games to 1. Okay, so now so then what is really interesting is why Go is different from chess. And essentially, Go is very, very much more complex than chess in a strictly mathematical sense. And it's because, now imagine, put your mind back to that tree of possibilities that you have in chess. And in a nutshell, the tree of possibilities that you have in Go is just enormously, enormously larger than the tree of possibilities you have in chess. Now, humans don't play chess by exploring this enormous tree of possible situations in the way a computer does. Humans play chess in a different kind of way. So, you know, you might do a little bit of thinking ahead and a little bit of exploration, but essentially what an expert chess player does is that they recognize good board positions, and they sort of do a kind of pattern recognition on what constitutes a good board position that they might reach. And that's why humans are you know, that's why top human Go players can play excellent Go, and why it's very, very difficult for computers to play excellent Go. And sorry, let me just take a little step back. So just to reiterate, in Go, this tree of possibilities is very, 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 very much larger than in chess. And what that means is that you can't use that brute force method that computers use of just searching through these many, many possibilities, because they're just too many of them, and you're just not going to be able to do enough exploration. So even though, this is 2016 that this landmark was achieved, so even though there's been this, so what is it, from 1997, so nearly 20 years have between Deep Blue beating Garry Kasparov and Alphago beating Lee Sedol, with all of the huge increase in computing power we've had since then, all of that increase in computing power is not enough to tackle the enormous combinatorics of the extra super astronomically large search space that you'd have to look through for Go. And it's because in Go, you have a 19 by 19 board. Actually, do I have a... I should... okay, so I should say a little bit about how Go, about the game of Go. So just go back to this one. So Go is played on this 19 by 19 board, and the idea, for those who don't know, is to place so one player is black and one player is white. You place your stones one by one, and stones don't move once they're placed. They can be taken off the board if they're surrounded, but basically once you put a stone down, it stays there. And the idea is to claim territory by surrounding your opponent's stones or surrounding an area of territory with your color. And that's the essence of the game. Now you can kind of see, because you've got 19 times 19 places to put your stone, so in the very first move, you've got 19 times 19 possibilities. And then the next move, you've got 18, you've got 19 times 19 minus 1 possibilities of what the next move is going to be. And if you compare that to chess, where at any point in the chess game, you've only got like maybe, 7, 8 moves perhaps that you can make. Whereas in Go, there's just many, many, many more moves. And because of the nature of this tree structure, you get this kind of mathematically, horrible exponential growth in the size of the tree. And so what that means is that it's just so much bigger, the search tree for Go, than for chess, that even despite Moore's law and all the extra computing power that we've got since then, you can't just throw computing power at it and search through all of these possibilities. Okay, so so just getting back now to how humans play chess, right? So humans play chess by sort of recognizing different patterns and having a more intuitive understanding of board patterns. And humans play Go in the same way. So Go players often talk about their intuitive understanding of the board and the aesthetics of the different positions. So the challenge is, if you wanted to make an excellent Go player, is to try to replicate that, because you've got no chance of doing it in this brute force way. You've got to try and replicate that distinctively human kind of intuition about board patterns. And that is what DeepMind managed to replicate, and that's why it's such a significant achievement, because it's a very, very much more human-like approach that they've taken to this intellectual challenge than was taken by Deep Blue back in the 1990s to the challenge of chess. And that gives the techniques that they've produced a much wider application, and it makes the achievement a much larger one. So I just want to go into so another thing is that, as we'll see in a second, I think I've got a slide on this, that AlphaGo even makes moves that you could call creative. So I'll talk about that in a second. So what I'm really interested in, what does all this mean for AI and for the future of AI? Does it mean that we're about to create human-level artificial intelligence, the kind of thing that we see in the movies, and are, the robots therefore about to take over? And the answer is no. But I'm gonna elaborate on that, right? Or at least I should say, not yet. Yeah, that's a more exciting answer, right? Okay, but I want to, because you're a techie audience, right? So I want to say a little bit about how how AlphaGo works in a little bit of detail. And the way it works is basically it uses 2 neural networks, and it still uses tree search. So we'll see that in a second. But it uses these 2 neural networks to cut down the amount of search that it has to do. And these 2 neural networks, so there are 2 neural networks, and one is called a value network, and the other is a policy network. And these are types of network that you use in reinforcement learning. So for anybody who knows this stuff out there, and basically. So one of the networks is going to learns what a good board position is, and the other network learns what a good move is, and these neural networks are trained in 2 ways. So the first way they're trained is using a huge database of human games. So games by Go masters have been played and recorded for a very, very long time. So there is an enormous database of recorded human games that are at a very high level. And by training this network on these human games, you can make the network so that it's able to take a board position. So the input to the network is a board position, and the output of the network is the likelihood for any move of a human expert making that particular move. So as you can imagine, this is really useful for cutting down the search that you have to do. So if you already know that there's only, in some particular board position, there's only like 4 or 5 moves that are worth considering because they're the really good moves, then you don't have to have that huge combinatorial explosion of possibilities. So that's one thing it does. It learns by being trained on all of these recorded human games. And then, in addition, it uses self-play. So it uses self-play. It plays against variants of itself, and just plays just hundreds of thousands of games against itself, and that enables it to refine both of these networks actually. So it can learn what constitutes a good board position, so one that will eventually lead to a win, and it can also refine this network as well if they choose to do it that way. So by combination of learning on human games and learning through self-play, you get these two networks, one of which is going to tell you for a ball position whether it's a good ball position or a bad ball position, so likely to lead to a win or not, and the other one that learns for any ball position what are the likely next moves. Okay, so that's really, really useful, and in a sense, this is capturing something of the intuitive understanding that a human Go player has when they look at the board. But it combines this neural network stuff with the classic kind of tree search that I've already described to you. In fact, it uses a technique called Monte Carlo tree search. And the reason it's called Monte Carlo tree search is because there's a random element to it. And the random element is that again, because this tree is still going to be very, very large, and it's really still infeasible to kind of try and explore the whole tree exhaustively. So what it does is it makes sort of random forays into possible games. So it plays out lots of different possible games, and it uses all of these rollouts to kind of basically add up the likelihood that a given position and a given move is going to lead to a win or a loss. Okay, so what it's doing, so it's using tree search that we've already encountered with Deep Blue, but it's using these two neural networks to cut down the tree, to prune it, so that it doesn't have to look at so many moves, and it doesn't have to explore so deeply because it's got a good way of evaluating a board position. So those two techniques are what it uses, and that's essentially how they managed to defeat Lee Sedol. Now, there are a couple of really interesting things about this. And the first one is that they're using a kind of reusable technology. So the technology that they're using here, so these networks are using deep learning, and you may have, I'm sure you've encountered the hype that surrounds machine learning at the moment, and most of the hype that surrounds machine learning at the moment as a technology is to do with deep learning. So that's learning with neural networks that have many, many layers, and where each layer learns basically a successively more, so they're kind of hierarchically organized, and each layer learns a successively more abstract set of features. And these deep networks have a huge number of applications, and in particular, there's a fair amount of attention has been got by the application of these networks to labeling images. So this is a Microsoft image classification system where it successfully manages to label images as, this is a horse and cart and a birdhouse and a forklift. Now, these things often get things wrong as well, and of course, when you read articles, then they only tend to emphasize the ones that they get right rather than the ones they get wrong. But nevertheless, this is a very powerful technology and is finding a huge amount of application. It's not just image labeling, there's a huge number of applications of deep learning. And indeed, the things like predictive texting or speech recognition or many really, really useful technologies can exploit machine learning and put machine learning at the heart. And this is why there's so much investment at the moment in AI, is because people see a huge future for machine learning as a technology you can embed in many applications. So that's why you have like a whole slew of startups that are being bought for very large sums of money who are applying machine learning in all kinds of creative and innovative ways. So that's one thing that's quite interesting about Alphago, is it's using the kind of technology it's using is a technology that has very wide application. It just shows how powerful that machine learning technology is. Now, it's worth just pointing out why this technology is so successful, or rather has become so successful, because the kind of machine learning we're talking about here with these neural networks the algorithms involved have been around for absolutely donkey's years. There's really very little, there are a few recent innovations, but the basic algorithms, in particular the backpropagation method, has been around for a very long time. And the reason it's suddenly become much more successful and therefore become a really viable technology from an investment point of view is there are two reasons. And the main reason is big data. It's because you can now train these networks on very, very large quantities of training data, very, very large sets of training examples. And it turns out that methods that really didn't work very well with, say, 10,000 examples, which seemed like a big number in the 1980s. If you've got 10,000 training examples, you think to yourself, well, if my technique doesn't work on 10,000 examples, it's never going to work. That was a totally false intuition. In fact, it turns out that techniques that didn't work on 10,000 training examples, well, if you give them 10 million, they work extraordinarily well. But in those days, it was just infeasible to provide 10 million, a training set of 10 million examples to these kinds of algorithms. Now, nowadays, it's not infeasible. The data is there. So in the case of image labeling, there are so many images are produced by people all of the time and put out on the internet. There's in Google and Microsoft and Facebook, they have access to enormous quantities of data. So they have very large training sets that they can train this stuff on. But you wouldn't be able to do this if you didn't have the computing power to do it. And this is the other element. So the other element of their success is graphics processing units. So GPUs, it's turned out that GPUs are extremely, have just the right architecture for large neural networks and for learning in large neural networks very rapidly. So you've got large amounts of training data, and you've got the computing power to process all that training data and apply these old-fashioned learning algorithms on all of that data. So that combination, that's the killer combination of the GPUs and the quantity of data. Okay, so just to emphasize, the whole reason that AlphaGo is so successful is because it too works on a very, very large amount of data. So it uses these deep neural networks, but it carries out this self-play, and that enables it to play many, hundreds of thousands of games, and that, in essence, is the large data set that it's trained on. It can kind of generate its own training set by just generating zillions of games. Okay, so this technology is reusable so there's another sense in which the technology that underlies AlphaGo is reusable. So it uses deep reinforcement learning, and so deep reinforcement learning is so this sounds like an extended advert for DeepMind, but I mean it's true that DeepMind are doing some of the coolest stuff around there at the moment, because what matters is the underlying techniques and methods and so on. So it's not meant to be like an advert for DeepMind, but they have done some very cool stuff. So one of the other really cool things they did a couple of years ago now was they built this system called DQN, which uses a technique called deep reinforcement learning, which learned to play these retro Atari video games. So, for example, Space Invaders, or Breakout, or Montezuma's Revenge, and all these, or Pong. So all of these retro Atari video games, and the point is that it learned to get good at these games completely from scratch, knowing absolutely nothing about what game it was even going to be given to begin with. So it would just be given the raw pixels on the screen and the score, and then it would just go, and then it would play, again, really millions of games. I mean, it does have to play literally millions of games to get good at these things, and that's one of the limitations of this technique. But eventually, it would get good. Whatever game you gave it, well, it's not quite true. I'll come back to that in a second. But many of the games that you would give it, it would get to a very high level of these games after a couple of days of just playing them. So this deep reinforcement learning technique, which is basically learning through trial and error. Reinforcement learning is learning through trial and error. And learning through trial and error is what animals do and babies in order to figure out how to get by in the world and do smart things. And it's an absolutely fundamental part of animal cognition. Associative learning is it's basically the foundation of animal cognition, and it's the kind of thing that you would want to put into robots as well. If you wanted to train robots, or you wanted robots to learn for themselves how to engage with the world. So again, it's a really, really useful and important technology. And this deep reinforcement learning is the bit that enables Alphago to do self-play. Okay, so I was going to say that not all games does it learn to do really well in. So there are some games where there are very delayed rewards, which it's not so good in. And those are the kinds of, that's the kind of frontier of where this kind of technology is, or one of the frontiers for where this deep reinforcement learning technology needs to improve, is where there's long delayed rewards. So for example, in the game Montezuma's Revenge, which is one of these games where you have to kind of, get a key before you can open a door, before you can get into a room and that kind of thing. So, and then you only get the reward at the end of everything. And we have our human sort of knowledge that we come to the game with, that, oh, there's a key, so maybe I need to use this key to kind of open a door. But these deep reinforcement learning methods don't have any of that prior knowledge, so they only know that anything good has happened when they get right to the end and get the reward, and that just never happens. So for those kinds of games where the reward is very delayed, then the current techniques are not so good. Okay. Now, the big question, though, is... Oh, no, that's jumping ahead. No, it's not jumping ahead. Well, okay, the big question is, well, what does this mean? So I've pointed out how very, very significant this achievement is, and I think it's, it deserved all of the attention that it got earlier in the year, because it's, it really is pretty amazing what they did. And I should just have a quick mention for the creative move. So one of the moves in game 3, I think it was a move that was made by Alphago, where all these commentators, these expert Go commentators, they've got all 9 Dan, common Go players themselves, and Alphago made this move, and they think, it just goes to show the limits of these computers. Stupid move, so it's made a mistake at last, and Lisa Doll's going to win now. But then, sort of 7 or 8 moves later, they realized that basically Lisa Doll had it. And it was a move that, as Fan Hui, the European champion, put it, no human would ever have made, a completely inhuman move. And the reason was that AlphaGo, in all of the self-play that it had done, had discovered a whole new kind of strategy that could be used. And in fact, now human Go players are actually starting to use this strategy. And so this is a really very significant thing. So there was a kind of creativity that, in a sense, but creativity in a very limited domain, in the limited domain of Go. And I'm going to come back to that whole issue of limited domains in a second. Okay, so now, does this mean that we're heading towards human-level artificial intelligence? Well, some authors, such as Ray Kurzweil, so they predict that human-level AI is going to arrive when the available computing power basically matches the computing power that we have in the human brain. And there's all kinds of ways we might sort of measure the computing power that we have in the human brain. But you can, the back of the envelope stuff, you can take the number of neurons that's in the human cortex, and you can multiply that by the amount of power that you need to simulate a single neuron to a certain degree of physical fidelity, using the equations that have been established for some time for modeling neurons, the Hodgkin-Huxley equations, say. And you can get a kind of back-of-the-envelope figure for how many floating point operations per second, how many flops you would need in order to simulate a full human brain in real time. And it's basically you need an X of, there are a lot of assumptions here, but give or take an order of magnitude, you need an exaflop of computing, so 10 to the 18 floating point operations per second. And well, we all know that computing power has been increasing according to there's an exponential trend, so in particular Moore's law, but actually a more interesting exponential trend in this instance is the exponential trend in where the world's fastest supercomputers are going. And so that's a continuing exponential trend. So here we can see on the y-axis, this is a logarithmic scale. This is 1 exaflop here. And this is, in fact, we've just got another data point just in the last couple of weeks for those people who are paying attention to this stuff. And the Chinese are, so this red one is the fastest one in the world, the number 1 in the world. And this is the Tianhe Chinese Tianhe 2, and it's another Chinese computer that's at the top now, and so it's gone up a bit. So just in the last year, and anyway, the point is that you just have to extrapolate this a little bit further, right? Just a little bit further. So even if you think Moore's law is going to run out and all of that, you just have to extrapolate this a little bit further to see that we're going to get exaflop scale computing in the early 2020s. You know, that seems very, very likely. And that's enough to simulate an entire human brain. So, you know, according to Ray Kurzweil and the argument of many, that means that we should get human-level AI by that time. And lo and behold, we're getting all these amazing achievements in AI software, such as Alphago and so on. So, you know, so does that mean that we're going to get human-level AI very soon? Well, I think the answer is no. I don't think that it does mean that at all. And that's because computing power alone is not enough for human-level artificial intelligence. So basically, if you delivered to me or any other expert on the planet a box that could carry out exaflop scale computing, and I could simulate 80 billion neurons or 20 billion cortical neurons on using this box, well, I wouldn't know what to do with it. I wouldn't know how to organize those neurons, or I wouldn't know how to arrange, how to harness this computing power. I mean, that whole kind of exercise in thinking about how much computing power do we need to simulate a human brain, that's assuming that we're going to do AI in a human, we're going to make a brain-like AI. So there are other options, right? So I might think, well, I've got enough computing power and I could do it another way, but however you look at it, I wouldn't know what to do with that much computing power in order to code up a human-level artificial intelligence, even if I was going to try and copy the human brain, because we don't know enough about the human brain and the way it's organized for me to be able to, you know, basically code up and organize these 20 billion neurons in the way to replicate what the human brain does. Or indeed, even less do we know how to use this exaflop scale computing to achieve human-level AI in some other way, you know, non-brain-like way. So this is really the question. How can we program general intelligence? And the big question here is, does progress in AI software match the progress in AI hardware? And in computing hardware, not AI hardware. Well, so there has been significant recent progress in AI software, and Alphago is a terrific example, but I don't think it's enough. And I want to say why I think it isn't enough. So this is where the advert for DeepMind ends, you see. So although, you know, these guys would largely agree, I think, with this diagnosis, there's still a long way to go before we get to human-level AI. So Alphago is quite clever, right? There's no doubt about it. So it exhibits even a restricted kind of creativity, and neither its designers nor the Go masters fully understand what it does. It's, you know, is remarkable in many ways, and it uses these machine learning techniques which have a wide application. So it's not just Go that the underlying techniques are good for; they're good for lots of other stuff as well. However, all it can do is play Go, and this is the essential thing. It's a piece of specialized technology. It's specialized AI. And like all specialized AI, it's quite clever, but it's not very clever. It can't do anything other than play Go. And it can't do anything like the range of things that Lee Sedol or Gary Kasparov can do. So, you know, it can't make breakfast, it can't hold a conversation, it can't play with a child, it can't learn to make a meal. There are so many, very, very many things that it cannot do that we can all, as humans, do with our general purpose intelligence. So thanks to our general purpose intelligence, then there's this vast range of tasks that we can perform, and moreover, we can learn completely new tasks from scratch, and we can even invent whole new tasks from scratch. And moreover, we do this in the context of complexity in the mathematical sense, which is vastly greater even than Go. Because if we think that in a game of Go you might have 19 times 19 possible moves that you can make, or fewer at any given point, well, in ordinary life, there are very, very many more possible moves I can make at any moment than that. For example, I could sit down and start playing a game of Go. The game of Go itself, I could decide to hoot my horn, you know. I could decide to make a joke about somebody hooting the horn, you know. I mean, just at any given moment, there are so many. I could start to get really pissed off, you know, and it's like shout at this guy, throw my microphone out of there, right? I mean, no, I won't throw the microphone out of there. So you know, at this very moment, right now, we can imagine an enormous number of actions that I could take, some of which are kind of innovative and creative and crazy. You know, I mean, I could take my microphone, I could walk over there and I could plunge it into your beer, you know, and we can all, yeah, so there's all kinds of things that I could do, right? And so everyday life is very much more complex in that mathematical sense, even than Go. And in the context of that enormous mathematical complexity, we can learn to do completely new tasks, a vast greater range of new tasks than even DQN can, just in the context of Atari, and we can invent whole new things to do. So it's that kind of so in order to be able to do all of that, we'd have to achieve artificial general intelligence, or AGI, as it's so called. Now, AGI, we really don't know how to build general intelligence into a computer yet. And, well, okay, so let me be absolutely clear. I am not for 1 second suggesting that we can't do this at all. On the contrary, I'm absolutely sure that we can create artificial general intelligence. And indeed, I'm pretty confident that we will do that one day, and most probably, you know, within this century, and most probably within the lifetimes of many people in the audience. I think it's, you know, it's entirely possible. So I'm not saying I'm certainly not saying that it can't happen, and I'm not even saying that it won't happen, or that it won't happen in the, you know, within 100 years. But what I am saying is that it's not around the corner. It's not something that's just about to happen. And this is a very important distinction to make that often isn't made in media articles that discuss this kind of thing, where you might get an article, you know, in the media that says, oh, you know, these guys at DeepMind have beaten the world champion at Go, you know, and that means to say that robots are going to take over the world any moment. You know, no, it doesn't. That is a non sequitur. I mean, for many reasons. But the first reason is that just because we can do something like Go, which is a fantastic achievement in AI, it doesn't mean to say that we're very, very much closer to artificial general intelligence. And of course, even if we were, then we'd have to hope that I am cautiously optimistic that even when this does happen, we'll figure out ways of making it safe. But we have to think about that issue. Okay, so what are the real conceptual barriers? There are a lot of interesting challenges to when I'm trying to characterize the conceptual barriers to achieving human-level artificial general intelligence, then I often talk about the 3 C's, and consciousness is not one of them. That's a whole other talk. Right? And I'm not going to go there. So the 3 C's are creativity, common sense, and concepts, or abstract concepts. Now, this is just my list of what I think are kind of the really important things. So creativity. First of all, I think general intelligence requires creativity. So the ceaseless tendency to try out new things. And it's the kind of thing that we see. I'm not really thinking of Mozart or Picasso or anything there. I'm thinking about a kid, a child who is playing with their Lego bricks, or playing with you know, shoelaces and string and paper and stuff. So the kind of creativity that we see in any child while they're learning how to deal with the world, that's the kind of creativity that we don't yet really know how to endow computers and robots with. And so the second C is common sense. So that's the ability to predict the consequences of our actions. So both the physical consequences of our actions and the social consequences of our actions. And of course you can get computers to do that to a certain extent, but we have nothing that matches the human ability to basically predict the consequences of what we're going to do. So for example, I imagined taking my microphone and going and dipping it in the beer there, in that pint of beer. So you can imagine what would. So first of all, you can easily imagine that actually it's going to fit. Yeah, it's going to fit. So we can, you don't have to measure it precisely. We can all pretty much see that it's going to fit. You can imagine the kind of like squelching noise it's going to make, and you can also imagine, the liquid all kind of like finding its way up into the inner insides of the microphone and causing all kinds of harm to the electronics, and and so on. So we can imagine those. You probably never thought of that action exactly before, but we can. Right, imagine this, right? So I dip it in. Right? You can imagine that that's going to flick the whole glass up, and the glass might shatter against the ceiling, or it might fly over here. You'd all duck, And so we can all imagine, this is like the weirdest action, right? And we can all pretty much imagine, we've never thought of this before, but we can all pretty much imagine the consequences of carrying out that action right away. And we don't have to have precise measurements of the positions of all the objects involved, and we can sort of have a qualitative understanding of what of this action and its consequences. We also understand the social consequences. There would be social consequences if I actually did this, right? And you would be pretty you'd be astonished if I did it for real. I always giving these examples in these kinds of talks, and one day I really ought to do one for real and see what But there'd be more sirens, and so we can imagine all of this. So common sense, and of course common sense and creativity go together, because you need the common sense to see that the creative actions that you're thinking of, that some of them are perhaps not such a great idea, creative though they are, but others are, whoa, that would be so cool. If I did that, I could make millions. So now the third thing is the ability to form abstract concepts. So the ability to be able to generalize and form abstract concepts that allow us to communicate with each other complex ideas. And so when we've been creative and we've discovered some sequence of actions or that would be very cool, then you don't want to have to think of it in terms of the individual muscle movements. You want to be able to kind of, so if you've got some new kind of web interface, then you don't want to that you thought of. You don't think of that in terms of the individual keystrokes that you are going to perform in order to set it up or use it, but rather we have these much more abstract concepts that we use to think through ideas and that we use to communicate with each other about ideas. So that's the third C. So we don't really know. Of course, people are working on these kinds of things, but we don't really know how to endow computers or robots with these three C's, and especially to get them to work in combination in order to produce general intelligence. So we're really not there yet. Okay, so I need to kind of wrap up. 10 minutes. Oh, okay. So there are various different ways that so earlier on when I was thinking about, suppose you gave me an exaflop scale computer and dumped one on my desk, and said, right, go for it, then I kind of alluded to the fact that there are different ways I might try to build human-level AI. So one would be to try to copy the brain, to do it in this very brain-inspired way. Another would be to engineer things completely from scratch, and the common analogy that's used there is with flight. So it turned out that when we wanted to create a flying machine you might want to copy nature and build something with flapping wings, and Leonardo da Vinci had some amazing drawings of these ornithopters, but it turned out that a better way of doing it was to have fixed wings and some means of forward propulsion. So don't copy nature. That turned out to be the right way to do things. With AI, with AGI, we don't know. Maybe the way to do it is to copy nature. It definitely works, but maybe the way to do it is to engineer things from scratch in a completely different way. In the case of AI, we don't know yet what the best way to go is. Or we might do a bit of both. We might kind of like mix and match. But okay, so so just to reiterate, so I do think it's possible. I do think it will happen one day, but I think there are, there are all these conceptual barriers between now and then. And indeed, I don't think we really know what the full set of conceptual barriers is. And you've seen my little set, my favorite set of 3, but I don't think we really know exactly what they are. And especially when you work, you start working on the details of these challenges, and then other challenges are thrown up. So I do think it's possible, but I want to be clear about the kind of time scale and the uncertainty involved. So I'm often asked, when I think we'll produce human-level AI that might take over the world or might lead to, abundance and utopia, whichever you prefer. And this is the kind of answer that I like to give. So I think that between now and so I first did this in the year in 2015, and then this looked really neat then. So my kind of geeky mentality likes it to be in kind of nice multiples of 5, but now we're 2016, so it doesn't look quite so neat. But anyway, so in the next 9 years, no, 10 years or so, then we can be pretty sure that there's going to be specialist AI with significant economic impact. So that's the kind of thing we're seeing in spades at the moment. All these amazing London startups like SwiftKey and Magic Pony that have been bought recently for very large sums of money. And of course, Silicon Valley is just totally full of this kind of these kinds of startups that are doing amazing things with AI. So all of that specialist AI with significant economic impact is going to happen over the next 10 years. Self-driving cars, personalized medicine, there's a whole range of personal assistants and of amazing things that are going to happen over the next 10 years or so. Now, but that's not human level AI. It's not general AI. So I think now between 2025 and 2040, I think human level AI is certainly possible, but unlikely. Do you know? Over the more as the last sort of 18 months have unfolded, and I have been kind of like revising this a bit. I think it's maybe more likely than I thought 18 months ago that it's going to happen before 2040. But I still think it's if I was to put a bet on it, I would say that that I'd say that it's unlikely to happen before 2040. But then again, I thought Brexit was unlikely. So. But then between 2040 and 2100. Then I would say that human-level AI is increasingly likely. Really is increasingly likely. Still not certain, though. So, I really don't think we know. And of course, if and when it happens, or indeed if it hasn't happened by then some people will be able to look back and say, "I told you so. I was right." But of course, somebody's bound to be right. And the truth is that they will just be the ones that got lucky in their predictions. And I think we have very little basis. I mean, some people have some kind of rational basis for making predictions. Kurzweil, his rational basis is by extrapolating computing technology and thinking about the computing power you'd need to simulate the human brain and so on. So he does have an argument. It's not just making up the numbers, but I think that there are so many uncertainties there that we really don't know. Okay, so I'm running out of steam actually, so I'm going to skip a couple of bits. Well, basically, there was a couple of slides about superintelligence. So about the possibility that once we achieve human-level AI, so one thing I do think is the case is that once we achieve human-level AI, we will get to superhuman-level AI pretty quickly. So if on that time scale, say in the year 2070 or 2030, we did achieve human-level artificial intelligence, then I think it wouldn't be very long before we had superhuman-level AI. And the reason is that you just need a little bit better hardware or a little bit more hardware to do things in super kind of fast, to do things super fast, and you're going to get something that's better than you just had, that's just through sheer speed up. And that's only the most conservative way of moving from human-level AI to superhuman-level AI. So I think that the difficult step is getting to human-level AI. Going from human-level AI to superhuman-level AI is going to be an easy step. So that's why there is some, rational. There is a rationale for thinking very carefully about what would happen if that really occurred. So Ray Kurzweil talks about the singularity, and I've just written a book called The Technological Singularity, which spells out many of these issues. And I just want to say very quickly what I mean by the technological singularity and why I think it's worth thinking about, even though I don't think it's something that's about to happen. So by the technological singularity, I mean a time in the future when these three things occur. So first of all, we achieved human-level artificial intelligence. Then this has led quickly to superhuman-level AI, and the effect on humanity is so great that it constitutes a kind of break in human history. We can really, like all bets are off about the fundamental structures of human society and so on. I think it would have very dramatic consequences if we really did get to this stage. So I do think that a major challenge of our time is to ensure that if this does happen, maybe it's 40, 50 years away, and it's not immediately going to happen, but if it does happen, then we want to make sure that it leads to a good outcome. So one where there is abundance and leisure, and where we abolish poverty and disease, and we don't increase inequality, and we don't bring about the demise of the human race in particular. That's quite an important one, and that's the thing that Nick Bostrom and so on have emphasized particularly. So I think that it is indeed very important to ensure that AI is safe and beneficial to humanity. So these are important issues. Okay, so just a quick summary. So AI is making significant progress, and Alphago is a great example, and its underlying AI technology has wide application, as we've seen. So it's pretty cool stuff. But Alphago, like all current AI, is a specialized technology. All it does is play Go. Although the underlying technology can be applied to other things, it has to be re-engineered, to be repurposed. And conceptual breakthroughs are required before we have human-level AGI. And I don't think we know if and when this will happen, but if it does, I think superintelligence will follow pretty soon, and we do need to ensure that it's safe and beneficial. So I have to leave you with a book plug. So I have a book on this, and for those who read Chinese, you can get the Chinese version as well. So thank you very much.